So let's try to understand some equations of hyperplanes in 2D, 3D, and ND planes. Okay. So as you can see, it's a 2D plane with an x and y, which we are seeing in the previous slides as well. So if we take a tuple with attributes a1 and a2, and x1 and x2 are the values of attributes, so the equation of a 2D space can be written in the same way as we have written like a line of expression, y is equal to mx plus c, like where m and then c are the slopes and intercepts. So similarly here we have w0 plus w1 x1 plus w2 x2. The idea also applies here the same way. So whichever is actually falling on the positive side is greater than 0, and then whichever falls on the negative side will be a less than 0. So the expression can be written as w0 plus w1 x1 plus w2 x2 greater than 0, and w0 plus w1 x1 plus w2 x2 less than 0 for those values which are less than 0. But whereas if you move to 3D plane, the way of looking at the 3D plane is something different, wherein you have an extra axis of x, y, and z axis. As you can see, the depiction here, the hyperplane is actually the orange one that is actually displayed on the image, which separates both the values, which actually differentiates the red and then the blue. However, the expression still remains the same. Instead of w0 in 2D, in 3D it goes with a 4 as values, ax plus by plus cz plus the d, which is actually the constant here, and then which is greater than 0. So we have seen for x and y in a normal linear plane, and then we have seen it in 2D, and then now it is in 3D. So the expressions, the idea is still remains all the way is the same. Equal to 0 when it is on a hyperplane, greater than 0 which is falls on the positive side of it, less than 0 which falls on the negative side of it. But the question comes, what happens if it is more than 3D space? Okay, what happens if the hyperplane is in an ND plane, so more than 3 dimensions? So in that situations, we take all those values and then sum it up. So that means you can see the formula here that sum of I values from 1 to d, and we will use the same expression that wi dot xi plus w0 is equal to 0. And the idea here also remains the same for those values which are actually falling on the positive side, which even if you sum all the values, then it should be greater than 0, and on the line is 1, and then less than should be always less than, in the sense that the negative side of it will be always on less than 0. So that's how the hyperplane in ND works. How about SVM in a non-linear space? So far we have seen if the data is arranged, or if the data is happened to be in a linear space, we can able to identify the lines and then the hyperplanes and then the margins, and then we can differentiate it, and then we can apply the margins, and then we can able to use those equations to figure it out. But what happens when it goes to a non-linear space? Okay, so there are two different things here which we need to understand before we actually jump into the non-linear space. One is the linear SVM with a soft margin, and a non-linear SVM. So let us try to understand about the classification, and then we move on to non-linear space. As you can see, the example over here, so if x1 and x2 are two instances, and we have a hyperplane which classifies wrongly both x1 and x2, as you can see that we have two, one is h1 and then one is h2. So h1, you can see that x1 value actually crossed the hyperplane to the other side, and then the positive value x2 actually crossed the plane on to towards the negative side of it. But there is one more hyperplane called h2, which actually identified that there are no crosses in between, but the margin of that h2 is comparatively very less. So which one to take? Okay, so this is where we actually have to understand about a soft margin approach. Okay, so H1 is more preferable than H2 because of higher margin, that is for sure. And compared to H2, H1 is less susceptible to overfitting. So if you try to if you try to less the margin, and then that means you're trying to overfit. So it may applicable for the training data, but when it tries to go for the test data, it might have a problem. Might be situations where the plus crosses the line of boundary lines and then the margin to the other side. So we need to balance that. So in order for us to balance that, we actually have to understand about a soft margin approach, okay, to avoid the overfitting. Okay, so let's look at what is actually the soft margin classifier does. The soft margin allows certain points of deliberately misclassified. So it allows the algorithm to deliberately misclassify. That means if any points that crosses the margin and then the boundary, it still allows, and then it still says that, okay, this is my best optimal line, and also the boundary lines, and this is my optimal margin. Okay. So why is it actually is doing? Because the data keep varying from a training to a test data. So if you try to find one hyperplane with a maximum margin, and then it may fit for the training, but it may be overfit once you try to test with the test data. So that's the reason why soft margin classifier is one would actually identifies and then says that, okay, there is a percentage of misclassification is allowed. But how much is it allowed? Okay, for that we need to understand a new concept called epsilon. We will come back to that, but let us try to understand how a bit more deep into soft margin classifiers. As you can see the picture here, there are two depictions here. On the left side you see the negative and the positive. So the negative actually crossed the hyperplane and then the other side of it. But having said that, it actually not crossed the other boundary line. It's still in the boundary line itself, whereas the positive points actually cross the boundary line here. In the next picture on the right side of it, you can see that actually the negatives and then positives have actually crossed both the hyperlines on the other side of it. So though we are trying to accept with the soft margin classifier saying that, okay, we can accept up to some variance of misclassification, but it is always a question of how much is the misclassification allowed. Okay. So the slack variables, which are called the epsilons, can help us to control that misclassifications. So we will see that how it helps us identify the margin and the hyperplane. So there are three situations that we have depicted in this one. Okay, a slack variable is used to control misclassifications. It helps you where an observation is located relative to the margin and hyperplane. Okay, so suppose you draw a support vector classifier in such a way that it doesn't allow any misclassification, then your epsilon should be equal to 0. That means there might be a chance that if you try to apply this in situations subjective to the data sets, it might be overfit sometimes. Okay, if you say that if it can allow or in between the 0 and then the positive 1, and then that means you are trying to allow, as you can see in the picture right side, the plus actually has crossed the boundary line, but it did not cross the hyperplane. It's just crossed the boundary line, but still it suggests that, okay, this is the optimal hyperline. So we still have the control of the epsilon here. Okay, you have to understand that point. But if you are trying to say that in a case 3 that epsilon is greater than 1, that means that it actually can allow for those situations where the data points actually crossed even the boundary lines from the other side as well. Okay, so this is how the slack variable actually gives us the percentage, not percentage, the possibility for us to have the control from the algorithm, that how much that you want me to control, how much that algorithm needs to control. You want to put it epsilon 0 or less than or greater than. Okay. So what will be the cost of miscalculation if we try to apply that? The same thing that we have discussed in the past also. The cost of misclassification is greater than or equal to the summation of all the epsilons of each data point. If let's say there are only one, and then probably your error percentage is less. If there are more, so there might be a chance of more that is misclassified. So It's a summation of all epsilons of each data point and is denoted by cost or C. Only you understand the notion of the slack variable, you can easily compare two support vector classifiers. So in the case that what we have discussed in the previous slide, you have two such kind of hyperplanes with the boundary lines, but you can able to differentiate which one will be the error is much lesser. So you can measure the summation of epsilons of both the hyperplanes and choose the best one that gives you the least sum of epsilons. So a few things that we need to make sure: the summation of all epsilons of each data point is denoted by cost C that we have seen. If the C is large, that means the miscalculation cost is large, then you are actually allowing larger number of data points to be misclassified. That means you are violating the margin. So you get a hyperplane where margin is wide, miscalculations are allowed, but the positive side of it is that you have a model is flexible, more generalizable, and is less likely to be an overfit, and it's a high biased. Obviously, it is a high biased one. So on the other hand, if you make sure the C is small, then you are actually forcing the individual slack variables to be small. That means you are not allowing the data points to fall on the wrong side. Well, the margin is narrow and there are few misclassifications, but the model is less flexible, less generalizable, and more likely to be an overfit to the situation. So in other words, it's a high variance. Okay, so this is how actually you have a control of C, you have a control of epsilon, which is the error control,